Welcome back to Chapter 6, students. We have developed our bones, and so now we've talked about kind of how we make our skeleton, how our skeleton gets bigger. Well, now we're going to talk about remodeling and kind of homeostasis for our bones. So you actually recycle about 6% of your bone mass each week. So your bones are kind of constantly making and replacing the older tissue with newer tissue. Spongy bone is replaced more often than compact bone. Spongy bone gets replaced about every 3 to 4 years, whereas compact bone is usually replaced about every 10 years. The reason we recycle our bone tissue is that the older bone is just not as resilient. It's got more calcium salts in it, so it's more brittle. It fractures much more easily, and so we kind of recycle the old tissue. We get rid of the older tissue and we replace it with kind of newer tissue, because the newer tissue isn't as brittle. It's much more resilient. It's got lots of collagen, and so it is much kind of hardier and less prone to fractures. So maintaining bone homeostasis and recycling of our bones really has two processes: remodeling and repair. We're going to focus on remodeling first. So remodeling is kind of a two-part process. It has deposition of bony tissue, but also something that we call resorption of bony tissue. So the deposition is the laying down of new bony tissue. The resorption is the kind of getting rid of the older, more brittle bony tissue. So this occurs at kind of both surfaces of our bones, both periosteal surface and the endosteal surface. So we're using the osteoblasts and the osteoclasts. The osteoblasts, with a B, are responsible for making new extracellular matrix, making new bone tissue. Typically, there are mechanical signals that will trigger when new bony tissue is made. We also don't make new bony tissue unless we've got sufficient levels of calcium, as well as the proteins that kind of bind and concentrate the calcium, and we have to have enough mineralization enzymes. If we don't have enough calcium, enough binding proteins, and enough kind of enzymes to bring in the calcium and really get it in there, then typically we will not make new bone tissue. The osteoclasts are the ones that do the resorption. So essentially they eat the bony matrix. They're kind of like diggers, like not a post hole digger, like a skid steer, right? Essentially they've got these kind of teeth on them, right? They've got that kind of ruffled appearance that they dig these grooves into the surface of the extracellular matrix, and then pump those grooves full of acids and a bunch of enzymes from the lysosomes that essentially just dissolve the extracellular matrix. Those calcium salts get acidized, become soluble, so the calcium can return to the blood, and then the matrix itself and the dead kind of osteocytes get eaten by some phagocytic cells typically, and then once the process has stopped for this particular point in time, the osteoclasts themselves will go through apoptosis. They will essentially implode, so that they're not continuing to weaken our bones. So remodeling occurs all the time. As you sit here listening to this lecture about remodeling, your skeleton is remodeling itself. But really there are two kind of control loops, control kind of processes, mechanisms that kind of determine when and where remodeling occurs, kind of if remodeling occurs. So there's a hormonal control, and then there's mechanical stresses. So the hormonal control uses negative feedback, and the hormonal control is based on regulating blood calcium levels, not actually concerned with the integrity of the skeleton, but since the major place that we store calcium in our body happens to be the skeleton. It's like the best place for us to get calcium. And so we're looking at requiring a very small amount of calcium. So we typically have about 1,300 grams of calcium in our body. Almost all of that is stored in our bones. But the amount in our blood is very, very, very tightly regulated by this little negative feedback mechanism. Typically about 10 milligrams per little deciliter of blood. And our bodies don't make calcium. We have to get it in our diet, so your mom is always telling you to drink lots of milk. We also require vitamin D in order for our intestines to absorb calcium. It's another reason your mom was always telling you to drink lots of milk or go out and get some sunshine, because vitamin D is made in our skin, but we need UV rays to kind of catalyze some of that. So this very small level of blood calcium, very, very tightly regulated. And the reason our body keeps such a tight control on calcium levels is it is super, super important. If you want your brain and your spinal cord and your nerves to function properly, you need proper levels of calcium in your body. If you want your muscles to contract so that you can move, or your heart to contract so that it can pump blood throughout your body, you need proper levels of calcium. If you want your blood to coagulate so that if you damage your blood vessels, you don't bleed excessively, you need proper levels of calcium. If you want your endocrine system to function properly, or if you want your thermoregulatory mechanisms in terms of sweat secretion to function properly, you need proper levels of calcium. If you want growth and repair, if you want mitosis to occur in all of the cells of our body that go through mitosis, you need proper levels of calcium. And so calcium is one of the most important molecules and one of the most important kind of nutrients that our body needs. And we do have to get it in our diet. We do have to eat it. Luckily for us, as long as we get sufficient levels of calcium in our diet, we can build up by depositing that calcium in our bony tissue. However, if the levels of calcium in our blood drop, let's say we don't get enough calcium in our diet, then our body is going to take the calcium for heart function, for nerve function, for brain function, from the only place that we have it, which is our bones. So it uses a hormonal loop. The hormone involved is called the parathyroid hormone. The parathyroid are these tiny little glands that sit on the back of the thyroid. So the thyroid sits in the throat, and on the back dorsal side of the thyroid are these very small, tiny parathyroid glands. And what the parathyroid hormone does is it increases your blood calcium levels, typically by just sucking it out of our bones. So here you can see, here's the thyroid. We're looking at the back of the thyroid. And you can see here are these tiny little parathyroid glands. If our blood calcium levels fall outside of our normal homeostatic range, that will trigger the parathyroid gland and the parathyroid glands to secrete parathyroid hormone. What parathyroid hormone will do is then go activate the effectors, the osteoclasts. And those osteoclasts will degrade your bone matrix, release the calcium into the blood until our calcium levels go back to normal. And this will continue until we have sufficient levels of blood calcium. This particular feedback mechanism is only controlling and concerned with the levels of your blood calcium. If they get too low, this will be triggered, and it won't stop until blood calcium levels are back to normal, and it doesn't matter if your bones get turned into Swiss cheese in the process. Functioning of the brain, functioning of the heart, functioning of all those other things. Yes, of course we want a strong, healthy, sturdy skeleton, but we need our brain and our heart to function. The thyroid itself makes a hormone called calcitonin, and at exceptionally high levels, calcitonin will decrease blood calcium levels. It will kind of encourage deposition of bone, but not at levels typically that we have in the body. So the main primary driver of controlling blood calcium and thus kind of activating this loop is the parathyroid hormone. So here you can see osteoporosis. You can see this is a nice micrograph of nice normal healthy bone. And you can see here we have an osteoporotic bone. It is just Swiss cheese, basically. The head of the femur, the neck of the femur really, it is one of the most susceptible places to osteoporosis. That's why vertebral fractures and hip fractures are very common in people who have osteoporosis. But as the video at the start of this chapter mentioned, if you have an osteoporosis patient, the kind of instinct is to be like, oh, well, I shouldn't exercise. But actually, a little bit of weight-bearing exercise is actually quite useful. And part of the reason that kind of weight-bearing exercise is useful is something called Wolff's Law, which we're going to get to in just a second. So let's talk about calcium again for a sec. Right? If you have, the reason, again, one of the reasons we keep such a tight control on our calcium levels is that if you have even slight changes, too much or too little, in our blood calcium levels, it can be really dangerous for the body. So hypocalcemia is kind of lower than normal blood calcium levels. Your neuromuscular system will become very hyper excitable, like you're just kind of like trigger happy almost. If you have hypercalcemia, high levels of blood calcium, then the neuromuscular systems become unresponsive. You're not reacting well to things. And in addition to that, you can also start to get the kind of deposits of calcium salts occurring in the kidneys, kidney stones, but also in your blood vessels as well, which can occlude your blood flow. So why is exercise a good idea when you have osteoporosis? The other thing that determines and regulates remodeling is mechanical stresses. Our bones tend to reflect the stresses, that the mechanical forces that they encounter. So the load of your body, or all of your body weight, is here on the head of the femur. And so the head of the femur then tends to bend along this kind of arc. It's getting all the weight of the body. You'll see this portion here is much wider and thicker than this portion right here. We have compression forces occurring here from the weight of the body and tension forces occurring here, kind of pulling forces, right? But at this point right here, the compression forces and the tension forces kind of cancel each other out. And so this portion of the bone is much narrower than this wider portion of the bone here, because it's reflecting more stresses. Think about even handedness, right? Right-handed versus left-handed. This is a great example. So here, the tennis player has her serving arm, she's constantly using. If you look at the cross-section of her serving arm versus her non-serving arm, her serving arm will actually have thicker, heavier bones because she's using them more. She's putting more mechanical force, mechanical stress on the serving arm. This is what is known as Wolff's Law. This is why it is a good idea to do some light kind of weight-bearing exercises even if you have osteoporosis. Like if you were to look at the bones of a fetus or somebody who has been long-term bedridden, they would be much more featureless than like normal healthy bones. Wolff's Law explains our handedness. So the bones in your right hand, if you're right-handed like me, are thicker and stronger bones than the bones in your left hand if you're a right-handed like me. If you're a lefty, your left-handed bones are going to be bigger and stronger than your right-handed bones. Now, of course, you couldn't look at your fingers and see a huge difference, but they will be different. The bones will be thickest where they are kind of facing those kind of buckling, kind of compression forces. The trabeculae in the spongy bone, even though the spongy bone looks like it might be more fragile, and it is more fragile than the compact bone, the trabeculae line up like bridge trusses. If you ever looked at the roof of a house, or if you ever looked at, say, the Verrazano Bridge in New York, the trusses that hold up the roof or that hold up the bridge, your trabeculae function just like that. And any place, when you look at the bone markings, when you look at those big trochanters, those maybe, say, the spinous process on the back of your scapula, the back of your shoulder bones, they have these big, thick, bony projections. And those bony projections are so large in those areas because we have heavy, heavy, very active muscles that attach to them. And so those places face a lot of mechanical stress, and they thus will get a lot of bone deposition in those areas. Wolff's Law. So 2 regulatory mechanisms for controlling remodeling. The hormonal control determines either if remodeling occurs, kind of whether, when it occurs, always in response to those changing blood calcium levels to maintain our blood calcium levels. But then the mechanical stresses will determine where the remodeling occurs. More deposition will occur in areas of high mechanical stress. More resorption will occur in areas of low mechanical stress. So the hormonal loop determines kind of when the remodeling occurs, if it even occurs at all. And then the mechanical stresses will determine where that remodeling occurs.